Okay. The concentration distributions in the solids and in laminar flow. So this is what is the topic of what we say transport phenomena. Okay, we say transport phenomena, and then let me actually write this again. So this is the uh, topic. Now, what is our interest? See, first of all, we should need to understand the shell balances. So that is what we have to look at. So in that particular context, if I come down, so the first equation what we need to understand or what we have to write is this particular equation, which is known as the mass flux equation. This NAZ, what you see here in the circled portion, it is known as the NAZ. NAZ is mentioned as the combined mass flux. It's a combined flux. So NAZ represents, what does NAZ represent? See, NAZ represents to us the, what do you call, number of moles of A that go through a unit area in unit time. So this is the basic part of the understanding of NAZ. Now, the equation what you see here, it says two things here. It is, this is the combined flux and this is the molecular flux minus C into dAB dou XA by dou. Generally, we generally represent this molecular flux. Let me remove this. Generally, we say the molecular flux is JA. So this is molecular flux. Okay. Then comes the convective part. That means XA into total flow of the total mass. So Ne into total XA will give me the total what do you call mass of the A. So this can be written as XA into Na plus Nb. But see, I'm not writing with respect to the direction here. So there is no Z here, there is no Z here, there is no Z here, or rather there is a Z which is introduced now. Because this actually has to understand through a vector notation. So flux, combined flux in a vector notation or tensor notation, whatever it is to be understood in that way. So the molar flux to the concentration gradient for the Z component. So say this is what it has been written. So it is written for the Z component. The molar flux for the Z component, if I say, it will come to NAZ. Okay. So generally this is written as the molecular level or molecular flux plus the XA into total N, that too that too we want in the Z direction. So this equation is a very important equation uh, in carrying out or developing the equations for the concentration profile. Now, what is the requirement to us? So what is that we need to uh, get when you want to actually do such derivations? So you need actually something called a relation between NAZ and NBZ. So if this relation is understood, uh, then the other things will be easy for us. Suppose say I say equimolar counter diffusion. So we write it as NBZ is equal to NAZ. Equimolar counter, it says counter diffusion. That means I need to write, probably equimolar counter means one is coming in the left to right direction, one is coming in the right to left direction. It should be very carefully written. And suppose say if I say only one component A is diffusing and B is not diffusing. So then we have one relation called as, that means NBZ would be equal to 0. This NBZ equal to 0, we substitute in this equation, and then you find, ultimately you manipulate this total equation, and then you have to get the equation for NAZ. That we'll see in the next video.